All right, guys, I'll take you through this procedure B here because it's often kind of blown out of proportion. I think because this equation is here and people see this and they're like, all right, I'm done. So I just want to go through and show you how to do this. So it says, referring to the top of diagram 1 and the chart of the electromagnetic spectrum in the appendix, label the red and blue ends of the spectrum wavelength lines. So this is diagram 1. We have colors here, and these are what are called angstroms. Okay. Now, there is an appendix in the lab book. Several of you probably don't have your lab book handy, but there is an appendix back there, and they are asking you to refer to it to figure out which of these should be red and which of these should be blue. All right, angstrom is a measure of wavelength. So I'll grab the appendix, we'll take a look, we'll see if we can figure it out. Okay, I apologize. I tore my appendix page of this out of my copy of my lab book, probably last year or the year before, but we really don't need it if you want to think logically about this. So an angstrom is a measure of a wavelength, and a wavelength is the measure of the distance between either two crests or two troughs. So this is a crest right here. There's a crest, there's a crest. So they'll measure that, and that is your wavelength. So when you have a larger number, so we have two numbers here. We have 4,000, I see 5,000, then we have 7,000, which we're really comparing 4,000 and 7,000. When you have a larger number for wavelength, that means you have more space in between the waves. So with that in mind and everything you know about blue shift, red shift, and the things we've been talking about the last couple weeks or so, the last week, which one do you think is going to be blue and which one do you think would be red? Yes?
I think blue shift would be on left and then red shift would be on right.
Right. So some people figure this out without ever looking at us. Some people just Google 4,000 angstroms is what color, and it'll tell you it's violet or blue. You could do that too. But yes, I prefer you guys actually know the concepts. The shorter the wavelength, the more hyper it is. So that's where we get our higher energy stuff, which is blue. And that's going to make this red. Okay, so we've just accomplished number 1 here. So it says, referring to diagram 1, which shows the laboratory spectrum hydrogen Balmer absorption lines, measure the wavelength of each absorption line and record your observations in report sheet 2. So that's a lot to take in here, but really what they're saying here is this is hydrogen in a lab. So when we say it's a laboratory spectra, that means we burn some. What we did downstairs yesterday, guys, is lab spectra. We're burning a gas. You're looking through a spectrometer. You're figuring out where the lines are, and that's it. We're not looking at a star. We're not looking off into space or anything. We're just looking at a gas on Earth in a controlled environment. That's what they did right here. So they say, please record these onto report sheet 2. So what we're going to do here, this is a scale here, guys. And they're talking about a Balmer line. You're like, I don't get what a Balmer line is. A Balmer is going to be one of these symbols here. So if I go to report sheet 2, which is actually on the next page, it looks like this. So here is our report sheet, and they want to know, here's our absorption lines for this hydrogen, and they want to know what is the wavelength in angstrom. So how you do this is you actually just find the symbol. So here's this little alpha, this little A thing here. I find that on here, which corresponds to right there. I'm going to take a ruler or some kind of straight edge and just going to draw it right up to here. Remember, it's Earth science, so close counts. So if I do that, here's 6,000, here's 7,000. It looks like there's 10 lines in between them, so that makes each one of these smaller lines worth 100. So it looks like I have 61, 62, 63, 64, 65, like 65, 50. So that's what I'll be recording right here. 65, 50, and then the symbol for angstroms looks like a little California Angels logo. It's like an A with a little halo over top of it. And then we're going to do the same thing, and I want you guys to do the same thing for the other 3 lines. So go ahead and do that. Okay, so once we're done with that, we've completed step number 2 here. So step number 3 says locate the hydrogen Balmer lines in the spectra of star A and label with the correct Greek alphabet letters. This is as simple as saying, they did one for you here. So here's that. B1 is saying, okay, what do I think this one is, what do I think this one is, and what do I think this one is? It's pretty obvious, right? And we're looking at hydrogen from a star now, so they're just saying, okay, now go ahead and make these match up just so we're all on the same page. And if you're not real good with Greek alphabet letters, just make it look, somewhat legible there. And we've done number 3 here now. This is 4. Measure the wavelength of the hydrogen B line in star A. Determine the difference in angstroms between the star's hydrogen Balmer line from report sheet 2 and the line produced in the laboratory. Record under wavelength difference in report sheet 3. Okay, so when we look at stars, we've said before that we see these same gases, but they're shifted. So they're really focusing on this one here. So you guys have already recorded what this one was here. So this was from the laboratory line. I'm just going to use a different color pen here so I can keep track of what I'm doing here. So now we're going to look at this one from star A. We're going to go up and measure this. And there is, a small difference between what we saw in the laboratory line and what we saw in the star. Now, mine's not perfect, but I'm going to go ahead and say that I'm going to say, based on what I drew here, and yours might be a little bit different, that we're looking at a difference of about 30 angstroms, somewhere around there. You might have 50, you might have 25, you might have 20, but again, if you're close, we're good. So this is what we're looking at here. So the hydrogen Balmer line I got here, this is a blue line, because we're looking at star A. It looks like it was 4,900 angstroms. The difference for me, I got about 30 angstroms, or what I estimated to be about 30 angstroms. The shift direction. Now, from our laboratory spectra to the star, did it shift to the red end of the spectrum or to the blue? Because here, my green one was my original, so my blue one's my star. Did it shift this way or this way?
To the red side.
To the red, yeah, it shifted to the red. So shift direction, you could say it's red shifted, or red shift is fine. And by doing that, guys, we've actually accomplished now number 4 and number 5. Number 6 says, use the equation below to calculate the radial velocity of star A. Radial velocity is how fast this thing's moving away from us. Okay, and this is going to end up being in kilometers per second. And it says, record and label your answer, report sheet 3, show all your work. Now when we get to this equation, like I said, this is in the past, if I don't walk people through this is when they sort of dip out and say, I can't do this, because they see a bunch of things that they don't recognize. But look, I want to show you a couple things. All right, you got your radial velocity is the stars we're solving for now. The difference in angstroms of laboratory and hydrogen Balmer line, you just actually figured this out. This was from right here. So that's your wavelength difference. All right, I'm just going to put that there. Wavelength difference from next page. Times the speed of light. Now the speed of light you don't have to solve anything for because it's a constant. It's 300,000 kilometers per second. Okay, so that's just already there. Divided by the laboratory, the hydrogen Balmer line of our laboratory spectra. You've already solved this. You solved it when you guys did this one here. What did you have for that one?
That one, I got like 40, 50. Yes.
Yeah, I think that sounds about right. So So you already have everything you need here. Now it's really just going to be a matter of plugging things in. And some of the units are going to cancel out too. If you're into unit analysis, I'll spare you that right now. But this was from report sheet 2. And this you get right there. So you have everything you need. So if I go ahead and start punching these things in here. All right, so I said I had 30 times 300,000 kilometers per second. This divided by, you guys said it was 4850. So I'm going to get a number of that. So the star is going about 1,856 kilometers per second, based on what you guys should have something close to that. And showing your work here, guys. So you cannot get, I mean, you have to solve this here, but this is also a point where students, I don't know if they just get a little lazy or whatever, but sometimes turn these in with this all blank, or they didn't know they're supposed to record your work, or the directions say to show your work here. So this is not hard to do because, again, I already have all my numbers. You guys see angstroms are going to cancel out. You can see this now that it's set up, and that's going to give you a velocity. A velocity is going to be measured in kilometers per second, so we're going to get the answer we had here, which is like 1,856 kilometers per second. It seems fast. It is space. Things do tend to move fast out there, so it's, to me, the number seems reasonable, and we're good to go. You guys will do the same thing for star B. Which is shifted a little bit more to the red spectrum, which does indicate, anyone know what it indicates? It's going away from us, and we said the more dramatic the shift, the higher the velocity. So because this one here, let's go back to this for a second, because I can tell if this one's, oh, maybe it's not actually, maybe star A, take that back. Looking at these, star A may be shifted a little bit further to the red end of the spectrum now that I look at it closer. So based on that, this should be going slower. So I'm just going to keep that in mind as a student, because that to me means that the next number I get should be smaller than this. If it's not, if it's way bigger, then maybe I did something wrong. But this next one should be a bit smaller than this. So go ahead and do that. Great. So once we're done with number 2 there, and we just checked with everyone here, they got a smaller velocity than they did for the first one. Which is exactly what we anticipated. So we're down to number 8 here, and it says, use diagram 2, which shows the absorption lines for selected elements to determine the composition of the sample of star spectrum on page 345. Record your answers in report sheet 4. I'm not being too critical of the person that wrote the lab, but to me, those directions are not complete enough to tell you what to do here, so I'm just going to show you what to do. This is a sample star spectrum. We got all these lines, and you're trying to figure out which one of these elements, or which group of elements are in the star. So how you do this is, if you're trying to figure out if Mercury is in there, you put your ruler here, try to keep it straight as best you can, and you go down and see if you have a line there. Like, it looks like I have this line here lined up, and then I go and see if the next line's there. Looks like this line corresponds. Go across. I'm just going to keep checking these lines and seeing if I have a line down below between Mercury and the sample star. 2 fat lines there. I see 2 fat lines down below. That's a good sign. Go all the way across. When I do that, I can reasonably assume that I have Mercury in here. Now, I record it over here. The symbol. This student spent too much time, in my opinion, sweating this